Hello, dear peers. My name is Luis Vasquez, a student of the IBM Advanced Data Science on COURSERA platform. And this is my final capstone presentation. My project subject is Wafer semiconductor failure detection. And the agenda for this presentation contains use case, data set, data quality assessment, data exploration, data visualization, feature engineering, model selection and performance indicators, questions and answers, links and contact. In my opinion, machine learning and artificial intelligence can be used in different processes of manufacturing products. For example, in the control of the quality of manufactured semiconductor wafers, specifically in the defect detection, where human visual inspection has been gradually being replaced by AI and ML algorithms. It has been studied that after some time, the human vision starts to not recognize possible defects due to tiredness of the eyes. During a conversation with one friend of mine, he explained me that they are using ML models to determine possible defects in the manufacture of semiconductor wafers. I found it very interesting and decided to research what information exists in the market about wafer data sets, and found one at Kaggle.com. The great question here is, can a machine learning model predict whether a wafer was a defect or not? What should be the accuracy? The semiconductor wafer dataset is located on Kaggle.com on the link below. It is in the pickle format, height rate of compression. The data set contains more than 811,000 wafers. And they have been classified, the defect types, in 8 different classes, and one type for no defects, called none. You can see in the table below each one of the labels: center, donut, edge lock, edge ring, lock, random, scratch, near full, none. There are great quantity of non-labeled wafers, more than 638,000. The data set is imbalanced. The minor class donut has only around 550 samples, while the larger none has around 147,000 samples. Characteristics. It contains 6 features: the wafer map, die size, lot name, wafer index, try and test label, and failure type. Three features out of the 6 are relevant for the data defect detection model. Wafer map contains a categorical representation of the wafer image in a matrix format of rows and columns. The failure type contains the label of the defect type. A try and test label contains the classification split in test and trial. Data exploration. In the data set, the most important features are the wafer map that contains a categorical numeric representation of the image in a matrix format, rows by columns, where 0 means no wafer area, 1 means normal, and 2 means defect. The failure type, which contains a categorical string label of the defect: center, donut, edge lock, edge ring lock, near full, random, scratch, none. The try and test label that contains the classification of the data set is split into training and test. From the original data set, all non-labeled wafers will be dismissed because they do not contain labels and the wafer map is all 0. The wafers labeled with no defect, none, will be downsampling to have about the mean of the quantity of the other defects. This slide will show the images of samples of the different defect types. 1 contains center and donuts images. 2nd, edge lock and edge ring. As you can see, edge ring is at the edge of the image. And edge lock is located in a specific edge of the image. Lock for near full and random, and 5 scratch and none. Data quality assessment 3. The data set contains more than 811,000 wafers. About 638,000 wafers are non-labeled, and these wafers will be dismissed. Remaining 172,000 wafers will be analyzed. Sorry. The data set contains wafer maps with different shapes, rows, and columns. Since it's not good for the model to ingest mix of wafers with different shapes, then it has added new columns to the data set called wafer rows, wafer calls, and wafer RCs in order to classify the data set by shapes. The data set was classified by wafer shape and total quantity of defects. Then it has extracted the top 3 of each one. As a result, it has found that most of the defect cases are in the wafer shape range of 25 through 28, shown in the table below. In this case, as you can see, the 26 by 26 has the larger quantity of samples. After dismissing all the wafers out of the shape range 25 to 28, the data set still is in balance. You can see the minor class donut has only 8 samples, while the larger has 2,403 samples. This issue will be resolved using augmented techniques. Feature engineering. Since the wafer defect distribution is still completely imbalanced, it was needed to add samples to the following defects: donuts, edge lock, edge ring, near full, and scratch. It has used the following augmentation techniques. 1. Rotation, flip up and down, flip left to right, and that is mostly used for images. And the second technique is the encoder-decoder. It has used this method that allows to generate massive quantities of new samples, keeping the original patterns. The model selection and performance indicators. The wafer data set is labeled, and the wafer map is a matrix of pixels of an image of a wafer semiconductor. Then, as per all the readings and labs during the course, the best option for the models are the CNN deep learning and the random forest. It has used the following performance indicators: accuracy versus epoch to determine which combination will get the best accuracy, confusion matrix, since it is costly to pass, a defective wafer as if it were good. It's very important the model predictions have the less quantity of false negatives, and recall to measure the coverage of the minority class, donuts. As shown in the plot, the accuracy increases as the number of epochs increase, and decreases as the number of epochs increase. The model was only iterated through 30 epochs due to some limitation on the quantity of hours of the framework. But it seems the model will perform better with the number of epochs greater than 30. Confusion matrix. As per the confusion matrix, the model performance is in general fine, greater than 97%, except for defects edge lock, where only 65% of the case matched. 11% was predicted as lock, and 4% as random, and 2.5% as a scratch. The other exception is lock, that 4%, 4% log were only 71% of the cases matched. 9.8% was predicted as random and 7.5% as scratch. And the third one, the random, were only 74% of the cases matched. 7.6% was predicted as log and 5% as scratch. Random forest. The random forest model was estimated varying the number of estimators and the max depth. The number of estimator of 150 and the max depth of 17 got the best accuracy, 0.888. But it seems that it can be improved with number of estimators greater than 150. Random forest confusion matrix. After the confusion matrix, the model performance in general is fine, more than 94%, except for the defects 1, log, where only 62% of the cases matched, and 18% was predicted wrongly as H-log. And second, the H-log were only 65% of the cases matched, and 22% was predicted wrongly as log. As per the classification report, the class 2 H-log got the worst performance indicator. Precision 0.73, recall 0.65, and F1 score 0.68. And the class 4 log got low performance indicators also. Precision 0.73, recall 0.62, and F1 score 0.67. For these two classes, the model confuses one to each other. The remaining classes, the indicators are good. Conclusion. Can a machine learning model predict whether a wafer has a defect or not? Yes. Questions and answers, links to the notebooks and contacts. You can see the notebooks for machine learning model at the link below, and for deep learning CNN also at the link below. And the contact email for questions and answers or general feedback is luisrbq@hotmail.com. Thank you for attending the presentation. Bye-bye.